Hi, so welcome back to lecture 17 of MA 221. This lecture is dedicated to series. So we'll mainly talk about this three aspect of series. The first one is basic notations, how to find explicit formulas for partial sums in certain cases. The second thing is how to determine a series is convergent or divergent. And third thing is some basic test to say that a series is converging or not. Okay, fine. Um, okay, so let me start by defining what infinite series are. So we know that sequence is basically infinite list of numbers, right? And series is basically infinite sum of numbers. So most of the time we denote the series by this summation n equal to 1 to infinity an. This basically means we are dealing with this infinite sum. Okay. Uh, so this is the general notation that we use. And now some examples are like this: summation n equal to 1 to infinity 2n minus 1. So here my an is basically 2n minus 1. And if I try to write the series, then it will look like if I put n equal to 1 in this, then it will be 2 times 1 minus 1, which is 1. For n equal to 2, my second term of the series will be 3. Third term is 5. Fourth term is 7, then 9, and so on. So that is how we just, instead of this, sum, we just write this short notation, which is like easy and convenient to use. Okay, the next example is 1 over 10 to the n, and n varies from 1 to infinity. So the sum is basically 1 over 10 plus 1 over 100 plus, say, 1 over 10 to the third, and so on. Okay. Um, I want to make a remark here. Um, so the first example, the first sum actually does not make any sense because that's divergent series, right? Because if you just add all the odd numbers, 1, then 3, then 5, 7, 9, and so on, you go till infinity, then you will not reach anywhere, right? The series, the sum will not be a finite number. And that's what we mean by divergent series. Okay. And divergent series kind of doesn't make any sense because the sum is not finite, right? We don't know what actually infinity is. Okay. Um, but the second example does make sense. Okay. And the series is convergent. So we'll see how the series 1 over 10 to the n varying from 1 to infinity converges later. And that converges to 1 over 9. Okay. Um, one note here is um, how to decide what's going on for a particular series, what we do often is we just look at the finite sums as we add more and more terms, and we try to justify or try to like guess, is the sum going anywhere. That is like one standard way to like look at certain series. Now we will define the n partial sum. The n partial sum of the series summation an is a sum of first n terms. So my Sn will be basically sum of the first n terms, a1, then sum a2, so on till an. For example, my S1 is just A1, S2 will be A1 plus A2, sum of first two terms. S3 will be sum of first three terms of the series, and so on. Okay. So you can see that we are trying to like make a sequence out of a series. So we have this series summation n equal to 1 to infinity, and then we sort of made a sequence out of that series. The sequence Sn will look like how? The sequence will look like this. A1, then the second term of the sequence is A1 plus A2, third term is A1 plus A2 plus A3, and so on. So see, out of a series, we have made a sequence. And then every discussion of the sequence that we have already learned will be applicable in the series as well, right? Because we have sort of rephrased our question of series into sequence, where the sequence is Sn. Okay, I hope you get that. Next, we'll define so we say that the series summation an converges to S, and write and denote it by this symbol S to be summation over n equal to 1 to infinity an if the sequence of partial sums Sn converges to S. Okay. And I know that how this S1, S1, S2, S3 will look like, as I just mentioned before. Okay, now some more information that I need to tell here is the sum is said to be convergent, and S is called the sum of the series. Okay, when the partial sum converges, then we use this terminologies, and if the sequence of partial sums does not converge, then the series is said to be divergent. Okay. One example is summation 2n minus 1. So this is basically 1 plus 3 plus 5 plus 7 plus 9 plus so on. Then here S1 is just 1. the first term. S2 will be sum of the first two terms. So 1 plus 3, which is 4. S3 will be 1 plus 3 plus 5, which is 9, and so on. Okay. So then Sn will be just 1 plus 3 plus 5 plus so on. The nth term is 2n minus 1. So sum of first n terms. And my claim is this series diverges. Why? Because now I can see that Sn, so look at here, Sn is bigger than, so I have replaced, instead of 3, if I replace it by 1, then Sn should be bigger than this, right? For 5, again, I replace it by 1. So all of the terms, first n terms, I replace it by 1. But 3 is bigger than 1, 5 is bigger than 1, 2n minus 1 is bigger than 1. Okay, so therefore, now my Sn should be bigger than this quantity on the right. And this is basically sum of 1 n times, so which is just n. And now if we take n to be infinity, right, then Sn will tend to infinity. So therefore, my sequence of partial sums diverges. And hence, my series also diverges. Okay, cool. Next example is summation 1 over 10 to the n. Here my S1 is what? S1 is basically 1 over 10 or 0.1. S2 is 1 over 10 plus 1 over 100, 0.11. S3 will be 1 over 10 plus 1 over 100 plus 1 over 1000, which is 0.111, and so on. So my Sn, the n partial sum of the series, will be like this. And this is 0.111, so on 1. This is n ones. And I can write it by 1 over 9, 1 minus 1 over 10 to the n plus 1. Okay. And now if I take n to be infinity there, then this quantity will vanish because this tends to 0 when n tends to infinity. So my answer will be 1 over 9. Okay. Now how I get this identity, because see, if I calculate, then my S2 is just 1 over 10 plus 1 over 100. Okay. Now what I can do is, this is nothing but this is coming from geometric series, I guess, but you can just verify this. So this is just 1 over 9 times 1 minus 1 over 1000, which is 1000 minus 999 over 9 is 111 over 1000, which is 0.111. Okay. Yeah, but there should. Yeah, let me take one more page and explain it, because it might be important. Okay, how do I get the formula? So Sn was 1 over 10 plus 1 over 10 square. So basically this is not actually correct. The formula should be this, I guess. Okay, so let me erase this and then write it properly. So Sn was this 1 over 10 to the n. Okay, now if I take 1 over 10 factored out, then it will be 1 plus 1 over 10 plus so on 1 over 10 to the n minus 1. Okay, now this is sort of like geometric sum. And you might remember that geometric sum will be, and I will discuss this later as well. This will come again later. So just know that this will give us the formula 1 minus 1 over 10 to the n over 1 minus 1 over 10. So this is just 1 over 10 times 1 minus 1 over 10 to the n, and then 9 over 10, which is 10 over 10 times 9, 1 minus 1 over 10 to the n. So this will be 1 over 9, 1 minus 1 over 10 to the n. So the formula for Sn is basically coming from the geometric sum. Okay, now for S2, if I use the formula, then it should be 1 over 9 times 1 minus 1 over 100, which is 99 over 100 times 9. Okay, and this is nothing but, let me get some space. This is nothing but 1 over 100, which is 0 0.11. And you can check that S2 is actually 0 0.11. So this is matching. Okay, so therefore, that's how we got the formula for geometric sum. And it will, as I said, it will come again later. So there you will get more about how we get the formula and stuff. Okay, the next is looking at some examples. So what about these two series? Does it converge or not? So if we look at the first example, it is summation n equal to 1 to infinity n over n plus 3. So this is basically my an. Okay. Now, what is S1 here? S1 is A1, which is 1 over 4. S2 will be A1 plus A2, which is 1 over 4 plus 2 over 5. And so on, S3, S4, and so on. Sn will be 1 over 4 plus so on up to nth term, which is this. But this is bigger or equal to 1 over 4 plus 1 over 4 plus 1 over 4 plus so on plus 1 over 4. Because all of the next terms after, A2, A3, A4, and so on, all of the next terms are bigger than 1 over 4. Okay, this an is basically increasing. Okay, so the first term is 1 over 4, second term, as it is increasing sequence, the an sequence is increasing, so therefore A2 will be again bigger than 1 over 4. But when I replace everything with 1 over 4 here, then I'll get this inequality, bigger than inequality. And this is basically n over 4, because there are n number of 1 over 4, and this tends to infinity as it tends to infinity. So therefore, you can see that the sequence Sn is diverging. So the series also diverge. The n partial sum sequence is diverging. So this is also diverging. Okay. The same kind of analysis goes here. Here S1 is 1, S2 is 1 minus 1, which is 0. S3 is 1 minus 1 plus 1, which is 1. S4 is again 1 minus 1 plus 1 minus 1, 0. And so on. So we can see that this n partial sequence of the series jump between 0 and 1. Let me just write here somewhere. Discussed later. Okay. Now, yeah, that's here. This jumps between 0 and 1, so therefore, obviously, this is not converging. And as this is not converging, the n partial sequence of the series is not converging, so therefore, the series will obviously diverge. Okay. Cool. The next thing is actually the divergent test that you might need to use solving some of the homework problems. It says, it's a theorem. It basically says that if the series summation an is convergent, then the limit of the terms, if I consider the general term of the series, then that term as a sequence should also go to 0. Okay. This is not an if and only if condition. So one way is true, but the other way is not. We'll see some examples later, but yeah. So note that this condition can also be replaced as limit modulus of an equal to 0, because if an goes to 0 as a sequence, then modulus of an also goes to 0, and the other way is also true. Okay, if the limit of an does not exist or is not equal to 0, then the series is divergent. Okay, how to prove this? Maybe why is this true? Because I know that an is just rewriting intelligently. I can write this as the first n sums, first n terms of the sum, and then subtract all the terms till an minus 1. Then I'll get an back, but this is Sn minus 1. And now if I take limit n tends to infinity to an, then that limit should be carried out like this. But if you take n tends to infinity, then Sn as a sequence should have the limit s, and so is true for the Sn minus 1 sequence. So therefore this is 0. So we can see that if the series is convergent, then of course the an sequence should go to 0. Okay, but we can use this statement a little bit smartly and say that if I find one series for which the term is not going to 0, then the series will be divergent, and that is the divergent test. So this example might be more helpful in light to that. So here, this is my an, right? This is my term an. Now, if I consider modulus of an, because there is minus 1 to the n, so there is a question about sign, and I don't want to go so deep into signs. So I'll take the modulus of an because I see that this condition and this is exactly same. So yeah, modulus of an will be just limit n tends to infinity, this n plus 1 over 2n plus 3. The minus sign will just go away. And then I know how to deal with this sort of sequence. I'll take n factored out from top and bottom, and then I'll cancel the n, right? I've already seen and solved this type of things. But now this is 1 plus 1 over infinity, and then, okay, this is slight mistake. And 2 plus 3 over infinity, which is just 1 over 2. Okay. So therefore, I see that my modulus of an is not going to 0. It's basically going to half. So therefore, the series diverges. Okay. Yeah, we know that this is not convergent. We know that this sequence is not going to 0. So therefore, an diverges. So one small thing that might be confusing to you is, what is a series? Series is basically infinite sum. Okay. What is the n partial sequence of corresponding series? I'll consider S1, S2, S3 as like finite sums of the series. You can think this as like taking snapshots of finite terms of the series, and that is called n partial sum sequence of the series. But if I just consider the sequence that is like in the sum of a certain series, then that is denoted by an. And that an is basically important for the divergent test For divergent test, what we'll do is we'll just take the modulus of an and try to check that if that is going to 0 or not. If that is going to 0, then we are good. But we cannot tell exactly that the series is convergent. So one more remark is divergent test only says that if the modulus is not going to 0, then the series is not convergent. The series diverges. That's it. Divergent test does not tell anything about convergent. It just tell you that if an modulus of that is not going to 0, then the series is divergent. That's it. As simple as that. Okay. Yeah, the next question is this. Does limit an tends to 0 confirms you that the series converges? Sorry. So the question is, if the limit an is going to 0, then summation an converges. Can you just say that? The answer is no. And this example will give us one counter example. So here Sn is just 1 over square root 1 plus 1 over square root 2 plus so on, sum of first n terms. And now I can write this inequality. We have already seen this type of things quite some time. And then this is basically n times summation, n times sum of 1 over square root n. So this is just this. And this is square root n, and this is going to infinity as n tends to infinity. So as the n partial sum sequence is going to infinity, so therefore the series, given series, diverges. Okay, but notice that limit n tends to infinity 1 over square root n is 0 as when considered as a sequence. So therefore, only the terms going to 0 as n tends to infinity does not guarantee us that the series will be convergent. Okay, fine. And divergence test is generally the first thing that we use, or generally the first thing that we use when trying to determine a series converges. Okay, the next thing is geometric series. So geometric series is this type of series, where A is a non-zero constant and R is also a, constant. And so this is basically A plus A times R. See, n starts from 0 here. So the first term will be A, R to the 0, which is just A, plus AR, AR square, and so on. It'll just continue. So this is the first term. And one more thing is each time you are just multiplying by R to get the next term. And the sum. Okay. And this is the formula that I was referring to there. So if you have this finite snapshot like this, A plus AR squared till AR to the n minus 1, this sum is basically A times 1 minus R to the n over 1 minus R, where R is not equal to 1. this formula I have used here to get this formula. Okay, cool. Sorry, here. So the geometric series states is like this. If modulus of r is less than 1, then summation n equal to 0 to infinity ar to the n converges to a over 1 minus r. And if modulus of r is bigger or equal to 1, then summation ar to the n diverges. So 0 to infinity. So just a quick example, if we have this series given to us, then this is basically, we can say this is geometry series, right? Straight away. And here my r is -12 and a is 3, right? So therefore my modulus of r is just half, which is less than 1. So therefore by the geometric series test, we can say that it converges to a over 1 minus r, which is 3 over 1 minus 1 minus half. So 3 over 1 plus 1 over 2, which is just 3 over 2, which is just 2. Okay, cool. The next example is this, where I can see that r is -12. So obviously modulus, and a here is 5. So obviously modulus of r is 2, which is bigger than 1. So therefore the series diverges by the geometric series test. As simple as I like it. The next example is a little bit tricky, though it's like a simple simple use of geometric series test, but there is a little bit trick involved. Okay, so the main thing is here, n starts from 2, not from 0. Okay, so therefore you have to like do some trick there. So I can write like this: 3 times 5 and then -2 over -5 to the n. Okay, same thing, just that I want n and also n in the power of 5. So therefore I just multiply 5 over 5, okay, to this. Okay, then this is nothing but 15 times summation n equal to 2 to infinity -2 over 5 to the n. Okay, now if I want to start from, say, n equal to 0 to infinity, then what I can do is I can take -2 over 5 squared out like this, and then it'll be -2 over 5 to the n minus 2, right? Okay, let me just do it in steps. So in the next step, what I have done, what I have just done is like I have taken -2 over 5 square, factored out, okay, because this sum is nothing but 15 times -2 over 5 square -2 over 5 to the third, and so on, right? So I can easily take this thing factored out. Okay, now this is nothing but 15 times -2 over 5 squared, summation n equal to 0 to infinity -2 over 5 to the n, right? This is basically a simple substitution of variable. Or if you feel uncomfortable with this, what I can do is I can take k to be n minus 2, okay? Then n minus 2 is k there on the top of -2 over 5. And now, so n starts from 2, so therefore now k will start from 0, right? When n equal to 2, my k is 0. And when n equal to infinity, my k is also infinity. So therefore I have just changed the variable, okay? If you feel comfortable this way, then you can use it, fine. But then this is basically a geometric series where your R is minus 2 over 5. See, this is exactly geometric series. R is that. So 4 over 25 is there. And now by geometric series, this will be 1 and A is 1, right? 1 over 1 plus minus 2 over 5. Okay. So 12 over 5 times 1 over 1 plus 2 over 5, right? And if you calculate this, this should be 12 over 7. Okay, so that's the answer. Okay, so that is everything about geometric series. Now the next thing is telescoping sum. So telescoping sum is is of this type of series. So this series is nothing but 2 over 2 plus 2 over 8 plus 2 over 15 and so on. So to evaluate the sum, what we can do is like we can use the partial fraction that we have learned in integration. So if you do the same thing, this 2 over n times n plus 2 can be written as 1 over n minus 1 over n plus 2. Okay, you can check it. Then my S1 will be 1 minus 1 over 3 by using this formula. Okay, because this is now an, right? This is my an. My S2 will be 1 minus 1 over 3 plus 1 over 2 minus 1 over 9. Again, by using that formula. So this is basically A1. This is A1 plus A2. And similarly, my S3 will be, which will be sum of 3 terms. 1 minus 1 over 3 plus 1 over 2 minus 1 over 9. Okay. So S1, S2, S3. So for 3, okay, this is 4. Bad. 4. This is 4 plus 1 over 3 minus 1 over 5. This is A1 plus A2 plus A3. And my S4 will be 1 minus 1 over 3 plus 1 over 2 minus 1 over 4 plus 1 over 3 minus 1 over 5 plus 1 over 4 minus 1 over 6. So I can see that there is some terms like repeating with different signs. For example, 1 over 3 is with minus sign there, and there is plus 1 over 3. And then the same goes for 1 over 4. So there are repetitions going on. So therefore, there should be cancellation. Okay. Some pattern is there, and for telescoping sum, you basically have to find the pattern. So to make the calculations more visible, easily visible, what I'll do is I'll take all the positive terms on one side in S4 and all the negative signs like this. So now I can see that this and this cancels with that and that. Okay. And similarly, if I do the same sort of thing as we have done for S4 with the S5, then I'll get 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 minus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6 plus 1 over 7. Okay. There I can see that there are 3 terms which are cancelling. So if I continue this, and now we know how the pattern will go. So therefore, for the nth term or the n partial sum sequence, this will be like this: 1 over n plus 1 over n plus 1 plus 1 over n plus 2. Okay, exactly the same sort of same sort of pattern is going on. So now there will be cancellation with all of these terms. So for the nth sum, that remaining terms are 1 plus 1 over 2 minus 1 over n plus 1 minus 1 over n plus 2. Okay. So if I consider the first n terms and sum them in the series, then I'll get this. Okay. And if I take n to be infinity in there, then I'll get 1 plus 1 over 2 as limit, and the answer is 3 over 2. This is the sum of the telescoping series. So summation n equal to 1 to infinity 2 over n times n plus 2 is 3 over 2. Sometimes what happens is that you will see that this same series with some trick. So if you have this series given to you, this is basically same as this. So therefore, you have to be a little bit careful. Okay, now one remark is the limit laws give us these three results, I'll say. If summation an and summation bn converges, they have two converging sequences, series, sorry, then the sum is also convergent. And the convergent and the new series, which is like formed by taking term by term summation. So say I have a1 plus a2 plus so on plus an as one series, and this converges, and so is like b1 b2 and so on this series. Then a1 plus b1, if I form a new series like this, a2 plus b2 is the second term of the series and so on, this series also will converge and converge to, say this series converges to A, this series converges to B. So therefore this term by term summation series will converge to A plus B. That is basically what's the result is trying to say. Okay. Okay, now one more example. So suppose we have this sort of series given, and the question is this converges? Is the sequence sorry, is this series converging? And if yes, then what's the sum? So I can make this series a little bit more nicer. So I can write this as this plus 1 over 6 to the n summation n equal to 1 to infinity. And then this is summation 1 over n square plus n equal to 1 to infinity. So this is, we have already dealt with this type of thing. This is basically telescoping series. And these two are geometric series. So if I just use the formula, this is nothing but 3 over 6 is just half. So 1 over 2 is fine. Then by using the geometric series test and the telescoping series, so these two are geometric series. So let me just do the geometric series with the common ratio as half, and the first term is also half. This is also geometric series where r is 1 over 6 and the first term is also 1 over 6. And this is basically telescoping series. I guess you can figure it out how I get the sum like this. And you just calculate the sum, you'll get the answer where the series converges. Okay, now the next question is, what's the reason why we need some more test to, to conclude that certain series converges or diverges? Because divergence, as I already told you, divergence test deals only with diverging series. We can't tell a series converges using the divergent test. Okay, so examples. If you have this series n sine 1 over n, then if I try to use the divergence test, where I'll first look at So whenever you have a series, the first thing is to check that the terms are going to 0 or not, the terms of the series. In this case, this is the terms are like n sine 1 over n. And this is, I can write this as this, okay, slightly in fancier way. And this is 1, which is not equal to 0, of course. And why that is 1, you need to use L'Hopital to figure it out. I'll leave it. And therefore, by divergence test, we can see that this is diverging. But what about this series, n over n square plus 1? Here, if I try to use the divergence test, then you can easily figure it out. Still, I'll solve it. Then this is nothing but 1 over infinity plus 1 over infinity, like this. Then 1 over infinity plus 0, which is 1 over infinity. And then this is nothing but 0 again. But divergence test does not confirm the convergence of this. The series. Right? We still do not know if this is converging or diverging. Okay. Though we have checked that the terms are going to 0. Okay. So therefore we need to like apply some other test to like confirm that this series actually converges or not. Okay, the first thing is the first test rather is the integral test. Okay, the harmonic series, which is a name of this particular type of series, 1 over n, which is just 1 plus 1 over 2 plus 1 over 3 plus so on. This actually diverges. Okay, and we'll see it later how. But the question is, what about the series summation 1 over n square, which is just 1 plus 1 over 4 plus 1 over 9 plus so on. Okay, what about that? So for the integral test, what we do is we just consider a graph, or we just consider the okay, so the question now is, this series converges or not, right? So the terms are 1 over n square. Okay, fine. But I can consider y to be 1 over x square, that function, right? This function is like this. If you look at the graph, the function is like this. Okay. Now at 1, if I consider this rectangle of say height 1 and width 1, then the area of this rectangle is basically 1. Okay. Fine. So far, so good. So 1. If I consider the second rectangle from 1 to 2, having say height 1 over 4 and width is also 1. So this is having the area, the second rectangle is having area 1 over 4. Okay, fine. And if we can continue to do that, then the third rectangle will be having area 1 over 9 and so on. Okay, and that is less than 1 plus integration 1 to n 1 over x squared dx. Now what's happening there? So why this right hand side is bigger than this sum? Okay, this sum is basically area of all of this rectangle, right? And so on, just go on. But what is 1 to n 1 over x squared dx? That is something else. The area of this thing is, okay, let me just clear it out a bit. So this thing is, so start from 1, so this area, okay. And obviously 1 is there, so therefore I'll just also include this. And obviously this red shaded area will be bigger than all of this area of these red triangles, right? Because red triangles are like discarding these small pieces, okay, and so on. So therefore, for sure, I can say that this bigger than inequality is valid. Okay. Now, what is this integration? It is easy to evaluate. This is basically minus x inverse, and from 1 to n. It's 1 minus 1 over n plus 1, which is 2 minus 1 over n. And when, and obviously this is less than 2. Okay, fine. So therefore, I can see that the sequence Sn is monotonically increasing. And bounded above by 2. So therefore, remember there is a theorem in sequence. So therefore, Sn converges. And as Sn converges, we can say that summation 1 over n square converges as well. And in fact, if you do some more further analysis to this, which is like right now beyond our scope, this is the sum, pi square over 6. Okay. So how nice it is, like you are adding infinitely many rational numbers, right? 1 over n square would be rational for each n, but then pi is irrational. So the sum of those infinitely many rational numbers will be irrational, which is interesting. Okay. Now the question is, what happened for the harmonic series summation 1 over n? I told you that that will be diverging, but how? So if I consider Sn for 1 over n, then that is just 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on. Okay. Now, my claim is this is bigger than 1 to n plus 1, 1 over x dx. How? Again, look back at the graph of y equal to 1 over x and then consider the rectangles. Now, what is 1 plus 1 over 2 plus 1 over 3? So this area of this like rectangle having height and width as 1 will be representing this number. And then if I take the height half and width 1 again, then this will be the area. That will be half again, representing the second number, and so on, along with the graph. Okay. But when you consider this integration, it starts from 1 to n plus 1. So starts from here. So, okay. So that integration is basically this area, this red shaded region. And obviously this sum is having this extra pieces, area of this extra pieces. So obviously, you know, the second quantity is smaller, right? This quantity is smaller than the sum. Okay, cool. I hope things are understandable. And now if I evaluate the integration, this is ln x from 1 to n plus 1, which is just ln n plus 1. And this again goes to infinity as n tends to infinity. So therefore, 1 over n diverges. Okay, sweet. But formally, what is the integral test? Suppose you have a function fx that is a positive function and which is decreasing in this interval. Okay, so see all of this function 1 over x is decreasing and always positive, and so is this other function. So therefore, in those two cases, we are able to apply the integral test. This is the precondition that we need to check before applying. We just can't, apply it anywhere. Then if the integration 1 to x fx dx converges, then the sum also converges. And if that diverges, then the sum also diverges. Okay, so not hard to remember. Okay, now, why is that true? Little justification that I want to make here. Okay, so now for a general, say, series summation, fn equal to 1 to infinity. This is, say, my series where I have just written fn instead of an, which is like totally fine. Then Sn is just f1 plus f2 plus so on till the first n term fn. Now that Sn is less than f1 plus integration 1 to n fx dx. Why? Because again, the same kind of logic goes on here. So if I consider this quantity, what is this in the graph? So if I consider 1 to n fx dx, then that is this area of this region, this blue shaded region. Okay, stops here. Okay, but f1, which is the area of this first rectangle, so therefore I'll also consider this. Fine. And why? So therefore, this blue box is the area of the blue shaded region. But now, on the other hand, what is Sn? Sn is basically area of this first rectangle. The second rectangle. Third rectangle, and so on. All of these rectangles. Why? Because I know that the first rectangle is having area f1. Because again, I can give justification to that. So if I consider the first rectangle, the height is f1 and the width is 1. So therefore, the first rectangle having area f1. If this height is like f2 and this width is again 1, okay, which is, of course, you can see, then this is f2. The area of this second rectangle is f2 and so on. Okay, so therefore things are in sync. Okay, so therefore every time I'm getting this portion extra when I'm considering this right sum. Okay, so therefore the inequality is actually making sense. Okay, now, and at the same time, Sn is bigger than 1 to n plus 1 fx dx. Again, you can do the graph and analyze what's going on there. I'll leave it for you. So therefore, 1 to infinity fx dx bounded implies Sn is bounded plus monotonically increasing. Why? Because, Sn, if the integration is bounded, okay, from this inequality, then this is finite as well as this. So therefore, Sn is also bounded by a finite number. Okay, fine. And at the same time, it is obviously monotonically increasing because all of this f1, f2, f3, fn are positive by the precondition. Okay, the function fx is positive function. Okay, so therefore all of these are positive. And when you consider s1, then you have f1, s2. For s2, it is f1 plus some positive quantity. So therefore, Sn is obviously monotonically increasing. Every time you go to the next term, say Sn to Sn plus 1, then you are adding something more. Okay. So, and by the theorem of sequence, if a sequence is like increasing and bounded, then Sn is convergence. Okay. And why the other condition? So if integration is unbounded, that means Sn is unbounded. And obviously monotonically increasing as well in this case for the same reason. But why Sn is unbounded? Because of this other inequality. If this is unbounded, then Sn is bigger than that. So obviously Sn will be unbounded. Okay, some examples. So now does summation 1 over n to the 1.001 converge? So I'll consider Fn to be 1 over n to the 1.001, not hard to guess. Now this is positive function and also decreasing. You can check this, not hard to check it. And now if I use the if I use the integral test, so always you have to like use the divergence test first. Divergence test says that limit 1 over n to the 1.001 goes to 0. So therefore, the first test for divergence is like gone. What do we mean by that? So therefore, this sequence may be convergent. Okay. So therefore, the next thing that we need to do is use the integral test. So if I use the integral test here, then this will be 1 over 1 x to the 1.001 dx. And this is improper integration. So therefore, you have to take t as the intermediate variable like this. And then you do the simple calculations. And at the end, you'll get something like this: limit t tends to infinity minus 1000 over t to the 0.001 plus 1000 over 1 to the 0.001, something like this. And that is basically 1000. So therefore, I can see that the integration is finite. So therefore, it is obviously converges. So by integral test, summation 1 to infinity, 1 over n to the 1.001 converges. Okay, so this is all about the integral test. The next thing is p-test. So before that, we need to define what is a p-series. A p-series is basically a series of the form this 1 over n to the p. Okay, that's it. For example, when p is 1, we get the harmonic series, which is just summation 1 over n. And we have seen that this is diverges by the integral test. And when p equal to 2, summation 1 over n square, which converges. Again, we have seen this by integral test. So the p-series test is if I have 1 over n to the p as series, then the series converges when p is bigger than 1, and for p less than or equal to 1, the series diverges. That's it. Again, a simple, test. Now, one example is summation n equal to 2 to infinity 1 over n ln n. So first, always you have to check divergence test. So 1 over n ln n, the sequence goes to 0. Right? Because I have n and ln n. So sort of like 1 over some big quantity when you just replace infinity in place of n. So therefore, the series may be convergent. Now use the integral test. So fn, if I take fn to be 1 over n ln n, then f is positive function and decreasing. Okay. So as n starts from 2, so therefore my integration also starts from 2 to infinity, 1 over x ln x dx. Again, an improper integration, so intermediate variable t, 1 over x ln x dx, and then take the substitution u to be ln x, then du is 1 over x dx, and thus this integration now changes to limit t tends to infinity ln x. I've just skipped a line basically. You can figure it out though, or rather I just do it. So this is limit t tends to infinity 1 over u du, I guess, to do. I'll not just write the thing there. Okay, so this is limit t tends to infinity ln u. Okay, but again I'll go from u to t, so therefore this is ln x from, what is the bound for t? T was from, oh sorry, bound for x. Okay, so I've used the substitution there, then did the integration, then change the u into x again, and then the bound for x was from 2 to t, so 2 to t, and limit t tends to infinity. Okay, then this is ln t minus ln 2, where limit t tends to infinity. And of course, this is just plus infinity because ln t goes to infinity. So therefore, the series is divergent. So summation 1 over, what is the c, n ln n, yeah, n ln n diverges by integral test. So in exam, you should write what you have used. Like the series diverges, but you have used the integral test to verify that. Okay, now the next example is summation n equal to 1 to infinity 1 over cube root of n square. So this is basically 1 over n to the 2 over 3, right? Summation n equal to 1 to infinity. You can use different things, but here p is 2/3, which is less than 1. This is basically a p series, right? And the series diverges, right? Because p series tells me that if my p is less than or equal to 1, then 1 over n to the p series diverges. So therefore, using p series test, we conclude summation n equal to 1 to infinity 1 over cube root of n square diverges. And that is it for today. If you find any difficulty solving any problem, any homework, you can email me or you can meet me in the office hour. Thank you.